We're here with Philip Wolfe, and my first question for you is, how did you get involved with optimization?
Ever since I was a kid, I wanted to be a scientist. For a long time, my principal interest was physics. I grew up in the Bay Area in California and lived in Berkeley. Shortly after I started college at the University of California. Physics was a big thing on the Berkeley campus in those days. The people on the Hill had a lot of Nobel Prizes and were celebrated. For any scientist, that made an attraction. I worked away on that for a while. But after I graduated, looked over my academic career, I was astonished to find that I effortlessly made a beautiful record in mathematics and had rather a struggle with physics. This partially decided me to go into the mathematical area. My interests were quite broad. I'd heard about computing machinery, and that sounded fascinating.
And this was in what year?
Got my AB in 1948.
Okay.
Made a trip to Los Angeles where they had a copy of the Bush differential analyzer, and I took a course in that. Maybe nobody knows what that is.
No.
That is a great big machine bed, about 20 feet by 50 feet, full of shafts, gears, and things. You set up the shafts to represent a variable changing in time, connect it with gears so that you can multiply it by a linear factor, put it into something called an integrator so that you can integrate the result over time, and in effect do derivatives. You can plug in a large differential equation into this machine and let it crank out graphically the answers to it.
So it was, in essence, it was an analog computer.
Definitely an analog computer. One was used very extensively during World War II, and probably the biggest drain on computing funds until they started with the digital machines.
Okay.
Well, I didn't pursue that very far. Actually, my main interest in mathematics were kind of in what you call the foundations. Logic, set theory, and meta-mathematics I found very fascinating, because they have the appeal of sort of getting down to the very essential ingredients of science. But I got distracted in 1949. I was a regular science fiction reader, and I have here a copy of Astounding Science Fiction magazine for October 1949.
Let me move back a little bit. And so there you're holding it up, and now I'm going to try to zoom in on it.
It's a pity the cover's damaged, but they always had some inspiration.
Let's see, I think I can get in on that date. There it is. Perfect. So we see that it was published in October 1949 for only 25 cents.
Yes.
Okay.
And this was the principal, almost the only outlet of good science fiction in that time. There's a story here called The Financier, spelled S-E-E-R. It's not much of a story. It's about a group of college professors who learn a new subject called the theory of games, and they use this to beat the stock market and build up the endowment for their university. I'd never heard of the theory of games. There's a little tiny two-person zero-sum game here used as an example. I was fascinated by this.
And so this is very interesting. This is the theory of games in a science fiction story in October 1949, and game theory was only a few years old at the time.
Right, yes. The von Neumann Morgenstern book was published, I think, first in 1945, and then the second edition in 1948. I was an avid game player. Chess, Go were my favorite board games. I played a lot of ping pong, too. But somehow the idea that there was a mathematical theory of games just absolutely fascinated me. I rushed out and bought the von Neumann Morgenstern book, started studying it, realized there was some real mathematics in this, and decided that that's what I wanted to do my graduate work in. It took me a while to find somebody who would agree that that was a reasonable topic, and there was just one guy on the Berkeley staff, Edward Barankin, in the statistics department, who done a little work in linear programming, was acquainted with the theory of games, and consented to act as my thesis advisor.
Now, when you're saying he was acquainted with linear programming, this would be in what year?
1949.
So now,
maybe early 1950.
Now, being in the West Coast, and the activity that Danzig was behind was happening on the East Coast,
Right.
and we didn't have the internet or other ways of communicating. How was someone like that able to find out what was going on in linear programming?
Barankin was basically an East Coaster. He took his A.B. at Princeton. Don't remember where he did his doctorate, but he maintained Princeton connections. At that time, he was pretty well acquainted with George Danzig.
Oh, okay.
And Albert Tucker and a number of the other figures in the field. Don't know what kicked him off in starting linear programming, but he was doing work in the mathematics of that. Taught a couple of courses in the Berkeley Mathematics Department. One was on convex cone sets and functions.
Okay.
And a couple of others on the basic mathematics. I and a friend of mine, Dean Gillette, both enrolled as students of his. Dean did a very nice thesis in repetitive games whose play is followed by one of a number of other games. I forgot now the official term for that sort of thing. Think of recursive games. It's a nice word there. I chose a kind of recherche topic. Games of perfect information, as treated by von Neumann and Morgenstern, have, of course, stop rules. They don't go on forever. And when they stop, the payoff is determined. My background in more abstract mathematics and set theory caused me to pose the question, what would happen if a game had no stop rule? Suppose you could play a game infinitely long. Of course, you'd have to have a referee decide who won when he saw this infinite sequence of moves.
Mm-hmm.
But as far as set theory goes, that's not a problem. I set out to investigate games of perfect information of infinite length. My thesis advisor was pretty sour about that. He didn't like the theory of games much anyway. He had some objections to the von Neumann and Morgenstern theory of utility that he felt was much too cramped and rigid to be a useful model of social behavior. I always tried to avoid discussions of that with him, but wanted to return to the mathematics, in which he wasn't very interested. But anyway, I posed that question, got some preliminary results, showed using a fair amount of set theory that games of infinite length and perfect information were not strictly determined, unlike games of finite length. That is, if I knew what your plan was, then I could win. And if you knew what my plan was, you could win,
Okay.
even though the games were supposedly perfect information. Much later in work that I haven't followed very well, that turned out to be something, well, I proved it using the axiom of choice. It turned out, as I understand, the proposition itself was more or less equivalent to the hypothesis of the continuum. Anyhow, it's way out there, it's
Okay.
As I say, my advisor didn't like it very much. But I pursued it to the point also looking for subclasses of games that would have a value in von Neumann and Morgenstern sense. Got a number of results. Then sometime in '53, I was startled to have a paper published by David Gale, and a student of his, in which they'd laid out the foundations of the theory that I was working on. And I thought I was scooped until I discovered that they said, well, now here's an interesting open question. And I'd already answered that open question.
Oh.
So Barankin had to agree that my thesis was publishable, and it was, and I did, and I took my degree in 1954. Meanwhile, back in 1951, Barankin did something really lovely for me. I think I was running out of funds at the time. My Atomic Energy Commission fellowship had expired, and I was looking very hard for something to do in the summer of 1951. He contacted George Danzig at the Pentagon and got me a job there for the summer. So I went from Berkeley to Washington, met George, met the group of people at Project Scoop, Scientific Computation Development Programs, under the Air Force in 1951, and I worked there all summer. George handed me a partially solved problem of trying to straighten out an algorithm for handling the problem of degeneracy in the simplex method. Degeneracy, when you have a lot of zeros on the right-hand side, has a theoretical possibility of cycling when you use the simplex method and then terminating. In 1950,
So just to give a background, we actually did speak about this with Alan Hoffman, but to keep this recording independent, we'll say that this is, at the time, nobody knew that the simplex method would actually work because there was a concern that it could go on and on forever.
right.
So the problem, as Danzig was giving it to Alan Hoffman, as Alan told me, was, is it possible that this could happen? And I think, with respect to the question he was asking to you was, well, if it could happen, could we do about it?
Right.
Okay.
Alan answered the first question beautifully by presenting us with an example in which the simplex method would indeed cycle on without ever coming to a stop. My angle on it was to read what little had been written about it, and there was a paper of, I guess, a student or at least an acquaintance of Danzig's, who had proposed a certain kind of perturbation of the right-hand side involving polynomials with little epsilons in them that was theoretically promising. What I did, and using something I'd learned from my study of logic, as a matter of fact, was to rephrase this argument in a very crisp mathematical form, using what is now known as lexicographic ordering of the elements
Right.
of the simplex method. And that sort of put this proposal on firm footing and gave a method that made the simplex method secure. If you use this procedure, it would terminate after a finite number of iterations. So that was a great summer in 1951. Hoffman and I settled both ends of this issue, and of course we met and we kept up a friendship ever since that time.
Now, when this occurred, the important questions were theoretical. To say here was a method for doing it. Did the lexicographic method then end up being implemented in the Project Scoop, or what was being in the coding that was being done at the time?
I don't believe it did.
Okay.
I don't know for sure. In my mind, it was. Well, it's kind of laborious. Quite a bit later, about around 1963 or so, it occurred to me there was a much simpler way of doing the same thing, which I then published. I believe I called it the ad hoc procedure, which really does perturbation but greatly shortens the work and actually is practical. And that has been used in a number of computer routines.
Go ahead. Go ahead, please. Go ahead.
And back in Berkeley in 1951, I slowly put together my work on the theory of games and included my work on degeneracy and linear programming as two parts of my doctoral dissertation. I got my doctorate in 1954. The other big sort of stroke of luck, or the nice thing that happened for my career, was also due to Ed Rankin, I think. He contacted Al Tucker at Princeton and recommended me for an instructorship there. For several years, Tucker and his associates have been very, very much interested in the theory of games. I was probably one of the very few potential instructors in the world who'd done anything in game theory at that time. So he hired me. And that was a terrific experience for me.
So this was at Princeton,
Yes.
and I guess starting in 1954.
Right. I was there from 1954 to 1957. At that point, as it happened, Tucker needed a right-hand boy. Lloyd Shapley, who worked for him for a couple of years as an instructor, and Shapley, I'll mention in passing, if it doesn't come back, I think is the second to von Neumann as most important in the theory of games so far. He'd left to go to the Rand Corporation. Tucker needed somebody to help out with a number of small tasks, and I happened to fit in that very well. So I worked quite hard for him for 3 years, and we developed a very warm friendship that carried on to the end of his life. Something that happened not before the end, not far before the end, was, I think, maybe for the first time I told Al what attracted me to game theory, namely the story of astounding science fiction. And Al said, oh yes, the author of that story got the idea from a public lecture of mine that I gave early in 1949.
Oh.
And Al said, as a matter of fact, I've got a copy of the magazine. Would you like to have it? And this is that copy.
Oh, okay.
I thought it was a wonderful,
Great way of closing the circle, right?
in a way.
So now, in 1957, when you left Princeton, you went where?
To the Rand Corporation.
And who was the group? What was the group there?
Danzig was a big attraction. There are a lot of really good people there. Shapley, Gale visited for a year. Other names possibly haven't got world renown, like Oliver Gross, Selmer Johnson, of course Ray Fulkerson. They were all there at the time and made an extremely attractive environment.
Now, was it a pure research environment, or were they
Almost entirely pure. George Danzig had, I think, the wisdom and the foresight not to rely entirely on the Air Force or on the scientific achievements, but had a lot of contacts in industry. And something I remember being kind of astonished by, but was sort of influenced my approach for a long time. It's just a little story that George told me in the very early days about going, I think, to, giving a speech before some consortium of oil companies in Los Angeles. And at the end of the speech, being practically awarded a contract or being invited as a consultant to work for them, and told how great his speech was and how little bullshit there had been in it. Because he presented what he thought linear programming could do in the way of improving production in an oil refinery. And somebody said, well, how much of an improvement do you think you could produce? And George said, oh, somewhere between 1% and 3%. And the audience felt, well, here's somebody who is certainly not bullshitting us. We believe that.
Right. Now, what would you say was the motivation for Rand to form a research group at the time?
I can't answer that question very easily. I was never that familiar with the with the whole structure of the Rand Corporation. It was set up as I understood it, as a research group given a great deal of freedom to decide what sorts of problems would be in the national interest.
Okay.
And I think maybe due in large part to John Williams, who was director of the mathematics department for a long time. They felt that, well, the theory of games had sort of an obvious potential military application. And certainly the sorts of things that had gone on in the Air Force and the linear programming area in the way of improving the efficiency of operations could be of great general interest.
Would you say, were there any applications during the early part of your career that you personally were connected with?
Uh, there were several. To a large extent, we were, I think, acted as free consultants to people from some industries. The oil industry was, I think, the big earliest source of interest. One connection I had for a couple of years that was kind of fun was with the Kern County Land Company. They had a herd of, I forgot the numbers now, of the order of 10 to 20,000 cows that they used for meat and milk, and of course had to feed every day. They came to Rand, and having heard about linear programming, asked us if we could help with the sort of classic diet problem. Their diet problem was their dietitians had a whole set of requirements about how much salt, how much protein, how much carbohydrate, how much of each of a whole bunch of ingredients their cow herds should ingest every week. And they wanted to go out in the market every week, take the current prices of the possible foodstuffs, and make the best deal they could.
Okay.
So for about a year, I was taking their weekly data, putting it into our computer, and giving them the answers about how they should feed the cows. And that was kind of fun.
Okay.
My own involvement at the Rand Corporation, and again, let me say what a wonderful place to work it was. Sort of the only requirement I was given was to do useful stuff, preferably in the areas of linear programming and game theory, even though that wasn't a strict constraint. And I took advantage of that to explore in quite a few directions. I had a real fascination with computing equipment. At Princeton, I made a connection with the Institute for Advanced Study Computer Project. That was the machine that was built from von Neumann specifications. An amazing machine in today's terms. It had a total memory of 1 kilobyte of 40-bit words.
Do you remember the name of it?
Maniac was...
Maniac, because I know there was a whole series of different names. Okay.
But formerly known as the Institute for Advanced Study Computer.
Okay.
And when you programmed for it, you took punch cards, now called unit records. Us old timers remember them, 80 columns by 12. And you punched your own program in binary on this card.
With a pencil, basically. Or did
they
have key punch
there's
machines?
a nice little punch. That,
there was okay.
Yes, it has 0 to 12 on it, and every time you punch it, the card moves over a line.
Okay.
And that's how you wrote your program, fed it in the machine, and see what happened. And it was a fascinating process. And even at that time, it wasn't very advanced. When I came to Rand Corporation in '57, I had to upgrade a lot of my understanding of computers. The IBM 701 had just appeared. There was a homegrown machine called Johnny-Ac that was one of the first transistorized computers, and I worked with that quite a bit.
Could you make any comments relative to the connections between the development of linear programming, game theory, and optimization, and the development of computers at that time? In other words, how much did math programming and optimization influence some of the developments that were occurring with computers?
Not at all to my knowledge. I was never aware of any influence from mathematical programming to the computer. We certainly used a lot of computer time, and economically maybe that helped boost the industry. But I'm not aware that.
Well, even in that sense,
I'm not aware that any design judgments were ever made to benefit work in mathematical programming. On the other hand, of course, you couldn't possibly do linear programming without a computer. Right.
I mean, it's one of the true practical methods that comes from mathematics, where people can say, look, it's saving a company money.
Yes.
What would you say, as you've been lived through the history of the field, what project or event has made you proud to be part of the field?
I can't think of any specific giant breakthrough. Oh, well, I guess I can reply again with some personal reminiscences.
Sure.
One bit of fun I had was deciding I wanted to really get into the computation of linear programming. What we had at that time was a pretty elaborate routine that written by Bill Orchard Hayes for the IBM 701. Very effective linear programming routine, written in machine language. I wanted to use it, and I wanted to get into its innards, and I absolutely couldn't understand it. It was way over my head, and maybe I was reluctant to learn that much machine language at that time to find out how it worked. Bill had just quit when I arrived in 1957. I think at that time he went to start the then forming company CEIR, Corporation for Economic and Industrial Research, that later Les Ford joined. In any case, he'd left, and I was to some degree given the responsibility for trying to do something about carrying on the software effort in linear programming. That George Danzig was very interested in carrying on, but not something that he was going to do personally. I worked on that code for a while and then finally gave up. I heard about Fortran, and it seemed like a wonderful idea. As we now say, a higher level language. You could write something like mathematics in it and have it translated. Nudged the RAND Corporation into installing it, and worked with it for a long time. Amidst the quiet sneers of my colleagues who were doing computing, they thought this was a very effete and probably very ineffective way to go about writing computer programs. I persisted anyway, and one of my great moments was after putting together linear programming code that I thought was pretty good, talking with friends at Standard Oil Company of California in San Francisco, who were bragging about an assembly language code they had that was very good. And I said, well, why don't you try Fortran? And I sent them the results of a test problem I'd run. They refused to believe it because I was getting a better time than their program was. But finally they checked it all out, and indeed I was. That was a time of great pleasure.
Right, sure.
Winning a race like that, which is really kind of outside of my field as a mathematician, was a real pleasure.
Okay. So you mentioned earlier the application that you worked on with the cow feeding.
Yes.
Was that your first practical application, or was the one?
Yeah, that was my first, and by golly, it was probably pretty close to my last.
Okay.
Almost all of my time was spent in trying to do algorithmic research.
Okay.
Find ways to improve the simplex algorithm. Do other kinds of programming problems. Probably one of the things that made it rather easy for RAND to hire me was work that I did in the last year at Princeton. And let me go back to this little anecdote. At Princeton, working on Tucker's logistics project, I and somebody else supported by the project, Marguerite Frank, started to look at nonlinear programming problems.
And this was about what time?
1955.
Okay.
And wow, there's so much history involved here. Let me go back a little bit farther.
Okay.
Bob Dorfman, an economist at Berkeley, had been interested in mathematical methods, economics for a long time, and worked with Edward Brankin, especially on the quadratic programming problem, with the quadratic objective function to minimize underlinear constraints.
Okay.
And Dorfman used the then very new Kuhn-Tucker theory for nonlinear programming to show something that was really kind of exquisite. If you wrote the Kuhn-Tucker conditions down together with the original constraints of the problem, you had a big set of linear equations that looked a lot like a simplex method tableau. And as a matter of fact, you could show that the solution of the quadratic problem was an extreme point of this tableau.
Okay.
It was really kind of exciting. The trouble is nobody knew how to find one of those extreme points. Unlike linear programming, we didn't have any regular way of getting there. Marguerite Frank and I devised a somewhat clumsy method of doing it, which has become known as the Frank-Wolfe algorithm. And while it's pretty poor for quadratic programming, it's turned out to have a lot of applications in other areas where you have a messy objective function under linear constraints. We submitted this for publication in the Journal of the Office of Naval Research, the Naval Research Logistics Quarterly. Alan Hoffman was an editor. At the same time, he'd received a manuscript from Harry Markowitz on portfolio selection and quadratic programming. And because these were both sort of similar subjects, he sent the Markowitz manuscript to me to referee, and he sent our manuscript to Markowitz to referee simultaneously. It turns out when I was talking to Harry later on, we both initially did the same sort of thing, looked at it, couldn't understand it very well, but it sounded like comparative mathematics, so we turned in our referee's report saying, publish this. Now, I had some twinges of conscience about that I think Harry didn't. I knew I hadn't really understood what he did. And about a year later, I went back to it and tried to really figure out what was going on. Now, I think I came close, but I was unfortunately struck by a creative idea at the moment. It sounded like he was doing something a little bit like the simplex method. And I wanted to see if I could model the steps he was taking in the simplex method. Well, I never made a perfect model, but I made a version of the simplex method to solve a quadratic programming problem. And that was kind of a breakthrough at the time. I remember sending a copy to Danzig at Rand. This was in very early '57. And I have his letter back saying, this is a terrific result, if it's true. I gather you omitted reading the proof.
Right.
But anyhow, I think that was part of the reason I was very welcome at Rand when I wanted to join there in 1957. So I worked on that algorithm and polished it some. The connection with Danzig was terrific for me. On another occasion, a couple years later, George would often call me in and just kind of rap about something that was on his mind. This day he told me about a couple of things, a couple of problem areas, something that Fulkerson had worked in, something else whose details I forgot. But in both cases, he was using the linear programming model and the simplex method on a problem that had a tremendous amount of data in. And he, in one case, Ray Fulkerson, in another case, had devised a sort of ad hoc method of creating the data at the moment it was needed to fit into the problem. After George told me about this, I reflected on it for quite a while and and it suddenly hit me that they were all doing the same thing. They're essentially solving a linear programming problem whose whose data, whose columns, I would say, being the important part of the data, were just too many to ever write down, but for which you could devise a procedure for creating one when you needed it, and creating the one that the simplex method would choose to work with at that moment. I won't try to go into more detail.
No, that was great.
Call it the column generation method. The immediate, lovely-looking application was to a linear programming problem in which you had a number of separate boxes for separate linear programming problems connected only by a small number of constraints. That fit beautifully into the pattern. It was a way of decomposing such a problem, so we referred to it as the decomposition algorithm. And that rapidly became very famous.
Right, and it's known today as Danzig-Wolfe decomposition.
Right.
And then even column generation methods today are still quite popular
Yes.
in applications.
Yeah.
So with the number of these contributions, what would you say is the one that would you consider your main contribution to theory and practice?
The two I just mentioned.
The Frank Wolfe algorithm and the Danzig-Wolfe.
Not so much that as the simplex method for quadratic programming.
Oh, okay.
And the word on decomposition.
Okay. Who would you say? What people in the field have you admired and why?
Been quite a few of them. Let me start with Albert Tucker. As I said, I worked closely with him for 3 years and then maintained a lifetime friendship. He's almost the only person I know who I can say was consciously and rationally good. He had somewhere hanging up in his head a code of ethics, a very nice one, and he observed it. I don't have a lot of anecdotes to give. You'd have to sort of know him and work with him to see it in operation. But you could feel that if he made a decision about something, that decision had nothing to do with the interests or passions of Al Tucker, but with whatever institution or cause he was working with. It would be in its best interest. Truly a really remarkable guy, and there are a lot of us who I think would pay him that kind of tribute. I know. Last August at the Founders Award ceremony, were you there?
Yes. That's what gave me this idea to do these interviews.
Do you remember Harold Kuhn's talk?
Yes.
And at the end of the talk, he gave a tribute to Tucker.
Yes.
He started to cry.
Yeah, it was very moving.
I think we all felt that kind of affection for him. But geez, so many other people. George Danzig, our acquaintanceship has been very long. At times it was a little bit stormy, but generally, like, say, in doing the decomposition work, we made sort of a perfect pair. George is a genius.
A modest one at that.
A modest one, but he has real originality.
Yes.
It seems to me when he wades into a problem, he's, and I mean this sincerely, unencumbered by the kind of baggage a lot of us are. He will sit down with the problem and let the problem speak to him in its own language, and he'll go to work on it. I, on the other hand, I had a wonderful mathematical education, and when I sit down on a problem, I start saying, well, what is there in my known bag of tricks that I can apply to this? So George has the new ideas, and in the collaborative work we did, I was the guy who could put the polish on it and put it in really nice mathematical form.
Well, it's interesting that you describe it this way because, your interactions at the time, which was 1960, 61, I think, was the decomposition work.
Yeah.
And later, he was my thesis advisor 25 years later. And I would describe the experience the exact same way.
Yeah.
Very similar way. Because it was even, then as, I thought that this was an evolution, but here you're describing it as this is how he had always been. And it's very interesting.
I'm sure of it, yeah.
If you could go back to your past and start all over again, do you think you would choose the same career?
Yes.
So where do you see our field going?
See, that's a tough one. I've seen our work in optimization become sort of an integral part of business planning, of industrial engineering, a very solid part. I can't imagine it's ever going away. Sometimes we wonder why it hasn't become more widespread, why more people aren't using it. But
Well, what do you think, I had as a question here, is what would you say has held optimization from being more widespread?
I don't have a firm opinion on it. It might have reached its natural limits of growth. It may be handling almost all the problems that are really worth handling with these particular tools. I haven't done a lot of consultant work here, but when I have, I've rarely found an area where I felt, that there was a tremendous gap that we could just wade in and fill. It seems to me that enough people nowadays know roughly the capabilities of optimization that there aren't a great deal of missed opportunities.
How do you describe optimization to someone who doesn't know what it is?
I give an example like cow feeding via the diet problem.
Okay.
Or a little more obscurely refer to twiddling all the valves in a refinery so as to get the maximum output. And then saying what you need are the equations that describe the operations of the refinery. And then you need a mathematical method that will tell you how to set the numbers for those valves in such a way to give the function its best possible value.
Okay. What would you say is
cocktail parties are held, though.
Well, I have like some stock examples that I use that seem to give people the picture of things, to recognize that it connects with daily life, from the things like airline fleet scheduling or crew scheduling, that what made that reason you flew on that plane was because optimization decided it should be that plane, and usually then that gives them a connection to how things are going. What would you say is the most invalid criticism of optimization?
I'll have to pass on that one. I haven't heard any criticisms for a long time.
Well, then let's turn the clock back. What would you say were the criticisms that you were hearing as the field was developing?
Oversell. A number of operations research practitioners just promising the world and thinking they could revolutionize the business if they had the right tools, and then finding out that you really can't.
And
it's maybe a little more, to me it was a little more dramatic in game theory. I think there was a time when a number of us felt it was really going to revolutionize life. The military would use it all the time. So would businesses. It would kind of drive society. On the whole, it's been a flop.
And why do you think that's so?
Because it can't answer enough questions. You do a great job on a zero-sum two-person game, but that's not what life really is. Life is a very large number person on zero-sum game, and people are still twiddling with solution concepts for that and still working on the theory of trying to get some rationality into it, and it hasn't been done.
So now that's with respect to game theory. Would you say the same types of things apply with regards to linear programming and other areas of optimization?
I don't think so much. I think probably most practitioners are really aware of such limitations as there are and how to use them. How to use the tool. As I say, I think there was perhaps a serious period of oversell in the operations search community, but my sense is that's died off now, and we kind of know how to use the tool.
Okay. And do you think that there's some valid criticisms of the technology?
Oh, gee, there must have been, but I don't have any stories that come to mind.
Okay. Would you say that there are some misconceptions then about optimization that exist?
Again, I don't think there's anything serious at this time.
Okay. So in some sense, you're saying time has made people learn more of what are the limits and realities of what we can do.
Yes.
Okay. Let's see. I think you have anything else you want to add? Maybe as some stories and this and that, because I love the way this went. I really am happy with it. Where you really gave a good flavor of what was going on. So, but I'm going to offer the opportunity for you to tell any other anecdotes.
I think I've told you all the ones I had prepared in
Oh,
advance.
okay.
And let me just summarize, I guess, by saying I am very pleased to have been there, to have shared in that excitement. The idea that the theory of games might spread over the world and solve all our economic and social problems, that was terrific. That was really inspiring. Oh, that reminds me just of one tiny anecdote. When I showed up in summer of 1951 at that job at the Pentagon, first thing I did was to go around for a couple of days and have short interviews with the other people in Project Scoop. And I remember going to the office of one economist, introducing myself, and wanting to sit down and talk to him. Well, he didn't want me to sit down and talk, and what he said was, look, I'm making a detailed model of the American economy, so you're going to have to excuse me because I'm terribly busy. We thought it could be done, I think. We had that feeling. It was very exciting. The theory of games, linear programming, and computers sort of all coming online at the same time was really a strong motivation. It was a lot of fun.
And you think you would, if you rewound the clock, you'd relive it in the same way, or want to?
Yeah. There are 4 or 5 results now. If you let me keep my present mind, I'd like to get them in print before somebody else does. But I think that's the only change I'd make.
Okay. All right. Well, thanks a lot. This has been great.
Thank you.